Hi, welcome back to the lecture series on microeconomics. We have been discussing theory of cost. Last time we have finished our discussion on the short run cost curves. Now we are going to see how we can derive long run cost curves. So in this lecture we are going to learn about long run total cost curve, long run average cost curve and some related concepts. So in the case of short run cost function, we have seen that total cost and average cost are the functions of the output level being produced by the firm. But in the short run there is one factor input which is held constant, rather than in long run all inputs are variable inputs. Now we can also say that short run is basically the period where the firm operates, and the long run is basically a planning horizon, because firm always plans for what is going to happen in near future. So now let us going to assume that we start with a short run case where the x2 input is the fixed input, and in the long run we are going to be able to manipulate the level of the x2 input. It implies that the firm is going to optimally choose the level of input 2 which is held constant in the short run. So now let us see how that is going to impact our cost analysis. So as usual I am going to start with a diagram before I introduce new concepts. So I am going to have a diagram where I plot the inputs along the axis. So x1 is the factor input which is a variable input in both short and long run, whereas x2 is the factor input which is held constant in the short run. So it is a fixed input in short run, but it is a variable input in the long run. So now let us look at the firm's equilibrium in this case. So let me draw the isoquant map here. So suppose I start with an isoquant level producing output Q naught, and we know how to derive the firm's equilibrium. We have to draw the iso cost line in this input plane such that it makes a tangent with the iso cost with the iso product curve or the iso quant curve. At some point it makes the tangent, say this is the point A, and at this level the optimal input combination is found, and the firm gets to know what would be the optimal level of input 1 and what would be the optimal level of input 2 it should hire or purchase to produce the quantity level Q naught. Now this is the short run equilibrium. Now note, as this is already done, this cost minimization exercise is already done by the firm. Firm knows these numbers, and once the firm knows, it locks the fixed input. So in this case let me assume that the fixed input x2 is basically capital, and we can also assume that, more specifically we can assume that this is plant size. So the firm has optimally chosen some plant size once it has targeted an output level Q naught, and then I say that this x2 is held fixed Okay. So, the plant size or capital is held constant at the x2 star level. Let me introduce a new notation here, and that is K naught, that is basically the plant size, right. So, now with this new notation of plant size, I can also write this plant size thing here, K naught, that is equal to x2 bar. Now, let us see what happens if the farm wants to expand its production level. So, of course, now we are not going to work with an upward sloping expansion path because this is short run. So, here let me draw this parallel to x1 axis line. So, now if the farm wants to produce higher level of output, say at level Q1, then it has to operate along this orange line, because I have already fixed the plant size or the level of my fixed input, which is capital, right. So, the farm then has to find its equilibrium, short run equilibrium though, at this intersection point of this isoquant and this fixed level of capital or plant size line, the orange line. So, you see that to expand output, now the farm can not tweak the level of plant size, but it can hire extra units of variable input, say x dash 1, and that is the way the farm will now produce extra output and expand. But note one thing, let us now look at the long run equilibrium of the farm if the farm is allowed to change both the inputs optimally. So, of course, the farm will then solve a Lagrange and we will try to find out a tangency point between this new isocost line which has the same slope. So, the new isocost line has the same slope as of the old isocost line. So, at this new equilibrium point B, the farm will optimize its production and then accordingly it will choose the input bundle. But note that as it is not allowed, then the farm is forced to operate at point C. So, if the farm is forced to operate at C, then we see that actually the cost of production is higher at point C compared to point B, because the isocost line which passes through the point C lies above the isocost line. Say, let me now denote this isocost lines. So, this is C naught, this is say C1, and let me now call this C1 prime, right. Okay. So, the isocost line C1 prime lies above the isocost line C1. That basically tells you that if the farm is in short run where it has to operate with a fixed plant size, then it can expand output, but that expansion cannot be done in a cost minimal manner. So, the farm has to pay extra, right. So, we can write the farm's cost function in this case as C equals some function g which is of defined over q and k. K is the capital or plant size, q is the output level, plus another function h which is defined over the plant size which is k, right. So, we are going to draw a diagram for the short run total cost curves. So, we are plotting output level along the horizontal axis and the cost in dollar terms, or rupee terms, whatever. So this is basically my total cost and short run total cost, of course. So now we know that this is a recap, but I think recap helps sometimes. So the short run total cost curve has two components. One is basically my fixed cost and the other one is variable cost, which starts from the origin and it has the inverse A shape. So if we vertically sum these two curves, then we get the short run total cost curve. So let this short run total cost curve is derived keeping some fixed value of some constant value of fixed factor input x2, and let me denote that as the K naught plant size level, right. Now there can be other plant size available, of course. So if that is the case, then let me draw a couple of alternative plant sizes which could be made available to the farm in short run, but the farm has chosen to operate with K naught plant size, and that can be like this. There can be, so let me assume that this is STC for a higher plant size and it takes value K1. Now we draw the third plant size which is even higher, right, something like this, right, and this is STC. So here the fixed input 2 plant size takes value K2. So here let me write down the assumption that K2 plant size is greater than K1 plant size and that is greater than the K naught plant size, right. So that is basically the assumption that we make. So basically what we observe, there are three different plant sizes which are possible to choose from, and for each of these plant sizes there is a corresponding short run total cost curve if the farm chooses a particular plant size, right. So now let me see how that has an impact on the cost. Suppose my farm decides to produce Q1 level of output. Let us see which plant size will be the most beneficial for the farm. Okay. So now we see that suppose there are intersection points with these three short run total cost curves. So here we have points like B, C and D, right. So you can see that if the farm wants to produce Q1 level of output with a plant size K naught, then the cost is AB, right. Now if the farm wants to produce the same level of output but for a higher plant size, then the short run total cost curve which is relevant for the farm, that is basically the red one, and that will give a higher total cost given by AC. So what we can see that for a lower level of output, if the farm wants to produce that level of output with a higher plant size, the total cost is higher because of the high fixed cost involved with the higher level of plant size. Now let us note that this story completely changes if the farm chooses to produce or decides to produce a higher level of output, say Q2 level of output, and then here you can see that to produce that level of output we have to move up to find the points on the short run total cost curves for different plant size. So again you see that if I draw a perpendicular line, that will create 3 intersections, and let me name them M N P. So this is say point M, then I call this point N, this is my O point and this is P point, say. So now you can see that for an output level Q2, it is beneficial for the firm if the firm does not stay with the plant size K naught, because that will give a higher cost of production MO. So the firm can optimally choose a plant size K1 which will give a less amount of cost Mn. So optimally the firm can go for a higher level of plant size which results into a lower level of total cost as given by the distance Mn. Now let us look at the short run total cost curve diagram. There we got a family of short run total cost curves. Each curve corresponds to a particular plant size. So what will happen to the long run total cost curve in this case? So let us draw the long run total cost curve in the same diagram. So if I do not produce anything in the long run, that is an option. So basically I will start with origin, so the long run total cost curve I have to draw in such a way that it becomes tangent to the short run total cost curves. Suppose we have a tangency point right here, say at point x, then there can be another tangency point between the long run total cost curve and the short run total cost curve for the plant size K1 at point y, and there is another tangency point between the long run total cost curve and the short run total cost curve for the capital size or plant size K2 at this point z. So this blue line, which is this broken line, that is basically a lower envelope of the short run total cost curves, and that is basically my long run total cost curve. So long run total cost curve is basically a lower envelope or boundary for short run total cost curves, and this long run total cost curve comes from the long run cost minimization exercise where all inputs including plant size is variable and the firm chooses all of its inputs optimally, right. So there is a corresponding diagram in terms of the average cost function or average cost curve as well. So let us look at that diagram. So we have quantity produced and we have cost measured in terms of dollar or rupee. Okay, so let me also write LTC here. So here I am measuring short run average cost and eventually long run average cost, right. So now let me assume that the plant has 3 alternative plant sizes as we have assumed earlier, and each of them will give rise to a short run average cost curve. Of course, if you have a short run total cost curve, you will have a corresponding short run average cost curve, right. So this is basically my SAC 1 that corresponds to my capital or plant size K naught. Then I have similar diagram, short run average cost curve 2, and this time it is for the plant size K1. Okay. Note that the minimum short run average cost has gone down for the higher plant size. Another short run average cost curve associated with the third level of plant size, which is denoted by SA3 and K2, right. So, these are basically my short run average cost curves corresponding to the short run total cost curves. Now, suppose the farm wants to produce some output level, say here, say Q1 level of output the farm wants to produce. So, now let me suppose the farm wants to produce Q1 level of output. Now, note that I can draw a perpendicular line through this output level to judge which plant size will give me the lowest average cost of production to produce this level of output in the short run. Now, it is quite clear here that to produce Q1 level of output, the farm will choose SAC2. So, it will basically choose K1 level of plant size, because at that plant size level the farm can produce Q1 level of output at the least average cost or at the minimum average cost. But of course, the same analysis as we have done earlier, if I now increase the output level, say Q, if the farm wants to produce a higher output level Q2 say, then if you draw the perpendicular line at that output level, we can see that the intersections with that perpendicular and the short run average cost curves say that it can be produced at the least cost manner or with minimum average cost with this plant size K2. So, we have to use the short run average cost 3 curve for that matter. Okay. So, here also we get a series of short run average cost curves corresponding to our choice of plant size. So, how to put a boundary on this family of short run average cost curves? So, now we can derive the long run average cost curve from the long run total cost curve that we have already derived, and this will be an U-shaped curve, and it will make tangencies with the short run average cost curves for different plant size levels at various points. So, the long run average cost curve is basically a lower envelope or boundary for long run total cost curves, right, and this long run average cost curve is deduced so LAC is deduced from the long run total cost curve, right. So, now we are going to look at the relationship between scale elasticity, which directly comes from the physical aspects of production technology, and these cost curves. So, we know that if the farm is on expansion path, then this condition will be met, right. okay, where F1 and F2 are the marginal productivities of inputs x1 and x2, and mu is basically the marginal cost. Right. Okay. So now we can definitely write from here W1 equal to mu F1 and W2 equals to mu F2, right. Okay. So now let us go back to our cost expression, which is W1 x1 plus W2 x2, and then basically if I now insert these findings in the cost equation, we get an expression like this. Okay. So now let us divide this cost expression by the output level to get the average cost, and then we have on the other hand right. Okay. Now note that this entity here is basically my scale elasticity of output that we have derived earlier while we were studying the production function and associated concepts, right. So from there I can now write okay. Now this can also be rewritten then as epsilon equals average cost of production, which is basically this, and the average cost is divided by the marginal cost, which is basically mu, right. So this epsilon now can take different values. It can be greater than or equal to or less than 1 depending upon the behavior of the average cost curve and marginal cost curve. So now let us look at various possibilities through a diagram. Okay. So remember that we are in the long run, so we are basically measuring output along the horizontal axis, and we are going to measure long run average cost curve and long run marginal cost curve along the vertical axis. Now we know from the analysis we have done so far that our long run average cost curve will be an U-shaped one like a cauldron, long run average cost curve, and then we have the marginal cost curve which is also U-shaped, right. If that is the case, then we can draw it like this, and we know for sure that the long run marginal cost or marginal cost curve passes through the minimum point of the long run average cost curve. Okay. So now let us concentrate on this intersection point. Let me denote this output level where the marginal cost passes the average cost curve. So the output level which corresponds to the minimum point of the long run average cost curve by Q tilde. So the output level less than Q tilde, for those output levels we observe the epsilon takes value greater than 1, right. And at this particular output level Q tilde, epsilon takes value 1, and finally when we have output level higher than Q tilde, then we basically have epsilon less than equal to 1, right. So, now let us write when we have epsilon equals to 1, we know that that means we have constant returns to scale, right, from our theory of production. Then when epsilon is greater than 1, then we have the case of increasing returns to scale, and when epsilon takes value less than 1, then basically we have the case of decreasing returns to scale. So, just let me write down here. So, this epsilon here is basically elasticity of scale. Right. So, then we can demarcate this area. So, basically all the output level, the range of output which is less than q naught, sorry, q tilde, that basically gives the increasing return to scale production function, and for all output level greater than the output level q tilde, we have the so called case of decreasing returns to scale. Only at this intersection point where epsilon takes value 1, we have the case of constant returns to scale. Okay. So, now we are going to look at a couple of special cases. So, suppose we have a conventional traditional form of Cobb-Douglas production function a times x1 to the power alpha times x2 to the power 1 minus alpha displaying constant returns to scale. So, that means that we are working with a linear homogeneous production function. Then in that case, how my cost functions are going to look like, that is what we are going to study next, because Cobb-Douglas production function is a very common form of production function and cost function which are used in applied production analysis. So, this case is for a CRS technology. So, there we can first plot the total costs both in short run and in long run along the vertical axis and output level along the horizontal axis. So, of course, first we are going to plot the various inverse S shaped short run total cost functions, say STC1 for a particular plant size. Then of course, we are going to have more. So, there will be a series of short run total cost functions for various plant size, right. So, if these are the different cases, then we can draw a straight line from origin which will be tangent to various short run total cost functions at various points. So, this ray gives me the long run total cost curve for a linear homogeneous production function which could be a Cobb-Douglas production function, right. Now, let us look at the average cost diagram. Q, now I am going to plot SAC and ALAC, right. So, here let me first plot my long run average cost curve, which is going to be a straight line that can be easily deduced from the long run total cost curve which we have just derived, right. So, LAC shall be equal to LMC in this case of constant return to scale Cobb-Douglas production function. So, of course, in this case we can have series of short run average cost curves displaying various levels of plant size, but note that so they will be tangent with the long run average cost curve, and it is the minimum point of the short run average cost curve which becomes tangent to the long run average cost curve. So, now we can draw another short run average cost curve corresponding to a different plant size, a higher plant size, and here it makes another tangency. So, basically we can say that the tangencies like point C and D will all lie along the straight line which gives the long run average cost curve in the case of a constant return to scale Cobb-Douglas production function. So, finally we are done with our discussion on long run cost curves. So far we have finished our discussion on various types of short run and long run cost curves. Now we are going to look at their implications while the firm chooses an equilibrium in the short run and in the long run. So we are going to continue with this discussion in the next lecture.